Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the course Analysis of Variance and Design of Experiments. So in this course we are going to talk about two aspects. One is analysis of variance and another is design of experiments. Sometimes you might have seen that these two topics are dealt in a different way, but the contents are nearly the same, and I personally believe that they are interrelated to each other. Well, when we are talking about analysis of variance, then it is simply a sort of test of hypothesis when we are trying to compare more than two parameters, and we are essentially interested in testing the equality of those parameters. Well, you might have done in the case of normal distributions, that when you are trying to take more than two samples and you want to test the hypothesis related to the equality of their means. But now the question is how this analysis of variance is related to the design of experiments. So in order to avoid this confusion, let me just give you a brief introduction. You see, whenever you are trying to conduct an experiment from the statistical point of view, then using the basic principles of design of experiments, we try to collect the data, and our objective is to test a hypothesis. So in this case, we have to collect the data as well as we have to test the hypothesis. So that is why both the things comes together. So now I have two options. That first I try to consider the analysis of variance. I try to give you the tool. And then after that I try to explain you that how the data is going to be collected under different types of conditions in which these tests can be applied. Or the second option is this, that first I try to give you the introduction that how the data is going to be collected, and then I try to explain you how are you going to use the statistical tool of analysis of variance. So I have to choose one of them because I cannot do both the things together. So I have taken a call here, and I have decided that first I will try to take up the issue of analysis of variance. I will try to show you that how the tools are developed, and after that once you know that how the tool have been developed, what are the conditions under which the tool has been developed, then it will help you in creating a framework that how are you going to collect the data, so that the assumptions what you have made, they are also going to be valid over there, because both the things are interrelated. Means you have to collect the data in such a way such that the basic assumptions of the tool, they are also satisfied. Right. So, in the first couple of lectures I will try to give you an idea that how the tools are developed, and then I will try to take up the issues of design of experiment, and then after that once you understand, then we can take care of both the things together also. So that is the way we are going to have this course. Now the second thing is how are we going to do this course. So what I have done, that I have prepared some slides in which I have tried my best to give you as much as I can, which I can handle here in the given time framework, and then I will be playing those slides on a computer, and then you can see here I have a special type of here pen with which I can write on my screen. So I will try to explain you, and I will try to give you the say mathematical proofs, derivations which are written in the slides also, and wherever I think that some more details are needed, I will try to explain you with my pen. So that is how we are going to proceed in this course, and the slides of this course, they are also available to you. I will try to show you here that that how they can be download it, what is the address. So, the best thing is that you can download these slides and you try to play these videos together. And whatever I am doing here, you please try to do it yourself, try to understand, and don't forget to read a book, because yes, this course cannot replace the knowledge that you can obtain by reading a book. And there are a couple of books which I have already given in the course homepage that you can follow any one of them. These books have been written from two perspectives. One that is application oriented, and that is the from the theory point of view. So, both are important, because if you do not know the theory, then you cannot develop the tool. And once you develop the tool, then you also need to know that how are you going to implement it. Right. So, it is something like if you want to develop a medicine for a disease, you need to know the biology and the medical science along with the chemistry and other subjects. But once the medicine has been developed and it has been approved by the competent authority that it can be used, then you also need to inform the user that how the medicine has to be taken. So, all these things together, they will move in this course, and I hope you will enjoy the course. And so, let us begin our lecture, and I will try to show you that how the things are happening. But in this chapter, what I am going to do, that first I will try to take some details which I will be needing to understand and to explain you the basic concepts of analysis of variance and design of experiments. So, definitely in the topics of analysis of variance, you have to do some mathematical analysis. So, for that you can use simply the values, or you can express those values in the form of vectors and matrices. So, I will be dealing here with both the things, and my objective will be to explain you how you can link both the things together, right. So, now we begin our course, and in this chapter I am going to give you a brief idea about the vectors, matrix theory, and some probability distributions which we are going to use in this course. Once I have developed these tools over here, after that I will simply refer you that we are using that tool to get this result. The problem here is that when you try to go through with the theory of vectors, matrix theory, as well as the probability distribution, this area is huge, and I believe that you have a good background in these topics. But the question here is this: what are the topics that you are really going to need out of that vast area? So, my very modest objective in this chapter, in this lecture and in the next lecture, is that to give you a quick detail about the tools which we will need to understand the basic concepts of analysis of variance and design of experiment. So, let us begin our course, and this is here the first slide, and I will try to show you how I am going to handle it. Okay, so, let us begin. So, you can see here that this will be the first slide where I am trying to give you here the title of the course, and this is here the chapter name, and after that this will be a number of lecture, whether this is lecture number 1, 2 and so on. And after that, what I am going to do in this particular lecture, that will be mentioned here. And you can see here now, using this pen I can write, for example, if I want to write my name, I can write down here Shalab, and write, and then my name is here Shalab, and I am from Department of Mathematics at Indian Institute of Technology. And after that, I have given you the detail here that how these slides of this lecture can be downloaded. So, they are uploaded on my home page, whose address is home.iitk.ac.in/tilde/shalab/sp. Right, and you can see here that I am writing with this pen, and here you can see that I have different options here that I can change the color of my pen. For example, now I can write my name in a different color and so on. So, this is how I will try to do it. Right. So, in case if you want to download the slides of this course, which are available in the PDF format, you can go to this address, or you can also scan this QR code. Right. So, in order to scan this QR code, you can take the help of any free application on your phone, and based on that you can do it very easily. Right. Okay. So, now my objective in this course is that I want to teach you that how you can develop the tools for the analysis of variance and design of experiments, and for that we need some basic knowledge to understand the topics in analysis of variance and design of experiments. So, I will be using some results on vectors, matrices and linear models. So, I am sure that you have done these courses in your earlier courses, but this will be a quick review that what are we really going to do here, and I am sure that you know most of this topic. It is just a quick revision, that is what you have to keep in mind. So, the first definition which we are going to use here is about the vectors. So, what is a vector? We are going to indicate it by, say, capital letter here y. So, this vector y is an ordered untuple of real numbers, right, and this vector can be expressed as a row vector or a column vector. So, remember one thing, these vectors are from the matrix theory, because vectors have been defined in different subjects in different ways, but we are going to deal here with the vectors that we try to define as row vectors or column vectors in matrix theory. So, for example, if I try to write down here this here capital Y, so this is going to be the collection of say this number y1, y2 here yn, and this is here an vector of order n cross 1. How? You can see here this is the first, this is the second, and this is here the nth element. So, there are altogether n elements, and which are indicated as a column vector here, right. And in case if you want to express the same thing in the form of a row vector, so the order of the row vector is going to be 1 cross n, and this is going to be indicated by y transpose. So, I try to write down here y, and I try to write down here a transpose sign. So, that is going to be a untuples y1, y2, yn. So, all these y1, y2, yn, they are going to be the some real number. Okay. And in case if you try to take all the values inside the vector, that is all yi's are equal to 0 for all I goes from 1 to n, then this vector becomes the collection of untuples in which all the elements are 0, and this is called as a null vector, null vector. And similarly, if I try to take here suppose 3 possible such vectors, they are of order n by 1 each, say x, y and z. So, you can see here these are x, y and z, they are 3 vectors, and so the elements of vector capital X, they are going to be indicated by x1, x2, xn. The elements of vector y, they are going to be indicated by y1, y2, yn, and the elements of capital Z, they are going to be indicated by z1, z2, zn. That will be our understanding. So, now in case if you try to add these 2 vectors, then we know from our matrix theory that you can indicate them by x plus y, and this addition is going to be element wise. For example, if I am trying to add here the 2 vectors capital X and capital Y, then the corresponding elements of x and y, they are going to be added. For example, you can see here this x1, y1 can be added, x2, y2 can be added together, and finally, the xn and yn can be added together. And we know from our knowledge matrix theory that if the orders of these 2 vectors are different, then they cannot be added. And similarly, this x plus y can be extended to here say x plus y plus z. So, in this case what will happen? X plus y plus z will become here the sum of corresponding elements x1 plus y1 plus z1, x2 plus y2 plus z2 up to here xn plus yn plus zn, and so on. And similarly, the subtraction also goes like as if you want to subtract x minus y. So, this is going to be x1 minus y1, x2 minus y2 up to here, say here xn minus yn. So, that you know. Now, similarly, if you try to say that k is a scalar, right, that can be positive or that can be negative, anything. Then in case if you try to multiply the scalar with the vector, then all the elements in the vector, they are going to be multiplied by that scalar. So the first element will become a k into y1, the second element will become k into y2, and the last element will become k into yn, right. So this is how we try to define here the vectors. And in case if you try to take these three vectors x, y and z, then in case if you first try to add y plus z and then try to add here x, so that is going to be the same in case if you try to add x and y first and when you try to add z, because you can see here that all the elements in this case they are simply going to be xi plus yi plus zi, right, for all I goes from 1 to n. So that you know. And similarly, if you try to consider the multiplication, so I try to consider here a multiplication where I am trying to multiply the transpose of a vector x with the sum y plus z. So this is going to be x transpose y plus x transpose z. And you can see here that these matrix multiplications are here possible because the order of the x here is n by 1. So the order of x transpose is going to be here 1 by n. Then x transpose y is going to be of the order 1 cross n and say n by 1. So this is going to be of order 1 by 1, and any vector of order 1 by 1, that is here a scalar. Right. And similarly, in case if you try to first multiply x transpose and y and then you try to multiply it by the scalar k, that is going to be the same as if you try to multiply the k and x and then you try to take its transpose and then try to multiply it by y, and that is going to be the same as if you try to first take the multiplication of k into y, then you try to take the transpose of x and then you try to multiply them together, right. And similarly, if you try to multiply this scalar on the sum of two vectors x plus y, then this is going to be k into x plus k into y. That means first you try to multiply the scalar on the individual vectors and then you try to sum them. And similarly, if you try to multiply here x transpose and y, so that we already have seen that this is going to be a valid multiplication, and in this case what is going to happen? We will have here a vector x1, x2, xn and here y1, y2, yn, and then the same way as we try to multiply the matrix, that this will become here this x1 into y1, and in case if you have here a second element say x2 and y2, so they will be multiplied and this process will continue till xn, yn, right. So this is how we are going to do this algebra on the vectors, right. Then we have a definition of here linear combinations, right. So in case if I have suppose a small m number of vectors say x1, x2, xm, and suppose this k1, k2, km are some scalars, they can be positive, they can be negative, then the linear combination of x1, x2, xm is defined as like this, k is equal to I goes from 1 to m, ki xi, this is called as linear combination of x1, x2, xm. So we are going to use it again and again, you will see, because this definition of linear combination is going to be very helpful when we are trying to develop the tools for the analysis of variance, right. Now the next concept which I am going to use here is about the linear independence, right. Well, you have learned the concept of independence in different ways. You have learned the concept of statistical independence of random vectors, as well as now we are going to talk about another type of independence which is called as linear independence, right. So this independence is related to the linear combinations of x1, x2, xm. So you can see here that in case if I try to take here x1, x2, xm as m vectors, and then we try to combinations. So, that will becomes summation I goes from 1 to m ki into xi. So, this linear combination is going to be said as linearly independent if there exist scalars k1, k2, km such that this summation ki xi is equal to 0. This implies that ki is equal to 0 for all I goes from 1 to m. Right. And if this does not hold true, then they are called as linearly dependent. That means, if there exists the scalars k1, k2, km such that at least one ki is non-zero, right, such that the summation ki xi is equal to 0, then this x1, x2, xm they are said to be linearly dependent. And then remember, any set of vectors containing the null vector is linearly dependent. Now, after this we try to understand the definition of a linear function. Right. So, if I say that I have got scalars k1, k2, km, and they have been represented in the form of a m cross 1 vector, here capital K. So, and then x here is another vector containing the value x1, x2, xm, and so capital K and capital X both are m cross 1 vectors, right, and capital K is a vector of scalars and capital X is going to be a vector of variables. Then in case if I try to take this form, that summation I goes from 1 to m ki xi, and if you try to see here, I have expressed this summation in the form of a vectors, right. So, if you try to see here, this k prime is going to be something like k1, k2, km, and x is going to be here x1, x2 here xm, and if you try to multiply them here, this will come out to be I goes from 1 to m ki xi, right. And this linear function helps us in representing several statistical functions in a very convenient way, which helps us a lot when we are trying to deal with the tools of analysis of variance. So, here this capital K, this is called as coefficient vector. Now, let me try to show you here the use of this linear function. So, if you try to see here, you know that in case if we have values x1, x2, xm, then their arithmetic mean is defined here as a x bar, which is here 1 upon m, summation I goes from 1 to here m, now and xi. So, if you try to see here, this I can represent in the form of our vectors. How? In case if you try to concentrate on this summation xi. So, this can be written here as say 1 upon here m, that will be as such, and this summation xi can be written as here say 1 1 up to here 1. So, these are here m values, and then I try to write down here all x1, x2, xm in the form of a vector. So, now this vector of 1 1 that is an order of 1 by m, and then this vector of x1, x2, xm, this is a vector of order m by 1. So, in case if you try to multiply them here together, you will get here summation xi, right. So, now in case if I try to write down this vector of here 1 by here 1 m. So, this row vector can be expressed here as a in the form of a m by 1 vector, say 1 transpose m, in which all the elements are 1s, that is unity. So, now this I can write down here as say here 1 m transpose and here x, right. So, this summation x bar now can be expressed here as say 1 upon m 1 transpose x. So, now you can see here that in your classes up to now you have just learnt this arithmetic mean to be 1 upon summation xi, but now I have expressed it in the form of say vectors, right. So, this is how you can transform the several such statistical function in the form of vectors and matrices. Well, one of the question that always crops up in the minds of students, sometimes they think that vectors and matrices are difficult to handle, but I will simply say this is only a myth. It is not correct. The fact is this, when you are trying to do simple calculation, simple algebra, then you can see the summations with your eyes. And the only drawback in vectors and matrices is that you cannot really see with your eyes that what is really happening. But I personally feel that if I can show you here that what is the relationship between the two and how you can express this functions like summation using the concept of vectors, then the life becomes very simple, right. Similarly, if I ask you that if you have to express summation xi square, how are you going to do it in the form of vectors and matrices? Now, let me try to show you here. Now, if you try to see here, I am trying to do it here. Suppose if I write down here summation I goes from 1 to here m xi square. So, do not you think that I can write down here is this here say x1 x2 here xm, and then here once again x1 x2 xm. So, the only difference is that you have to see here for the orders of the vectors. So, you can see here this multiplication is valid only when the first vector is of order 1 by m and the second vector is of order m by 1. So, when you are trying to multiply them here, the resultant quantity is going to be summation xi square, and this is a scalar quantity whose order is going to be 1 by 1. So, that you can see here you are getting here by such an expression. So, you can see here that all such functions can be expressed very easily using the concepts of vectors and matrices. The only thing is this, you have to be watchful and careful that the multiplications and different types of matrix operation, they are being done using the rules of vectors and matrices, and that is what I am trying to explain you here. Now, after this one more definition, which is about the contrast, right, or they are also called as linear contrast, because we are going to consider here a linear function. So, in case if you consider here a linear function summation I goes from 1 to m k I x I, which is expressible as k transpose x as we just understood it. So, this linear function is called a contrast in x1 x2 xm if summation I goes from 1 to m k I is equal to 0. So, this means you are simply trying to sum up the elements of your coefficient vector, and if this sum comes out to be 0, then you can say that this linear function is a contrast, right. So, for example, if you try to take here the linear function here x1 minus x2. So, you can see here that this can be expressed as a coefficient vector in which the elements are 1 and minus 1, and the vector here x with two elements say x1 and x2. So, this can be written as say x1 minus x2, and if you try to sum here this the values of coefficient vector 1 minus 1, which is here is 0. And similarly, if you try to take this second example here 2x1 minus 3x2 plus x3. So, in this case the coefficient vector can be written as say 2 minus 3 and 1, and x vector can be written as say here x1 x2 x3, and you can see here that the sum of these elements in the coefficient vector, which is here 2 minus 3 plus 1 is equal to 0. Similarly, if you try to take here this third example in which the linear function is x1 upon 2 minus x2 plus x3 upon 2. So, this can be written as say the coefficient vector 1 upon 2 and second element as minus 1 and third element in the coefficient vector as say here 1 upon 2, and then here this vector here x becomes here x1 x2 x3, and if you try to sum these three elements in the vector k, this comes out to be 0. So, all this one, they are the linear contrast. right. So, either you call as contrast or say linear contrast, we are going to deal only with here the linear contrast, because they are coming from the linear functions. Now, two more results for you that you can actually cross check and verify. I am sure that you know about them, that these contrasts, say x1 minus x2, x1 minus x3 up to here x1 minus xj, they are linearly independent for all j going from 2 to m, right. And the second result here is that every contrast in x1, x2, xm can be written as a linear combination of m minus 1 contrast like x1 minus x2, x1 minus up to x3 up to x1 minus xm, right. So, these are very standard, and I am confident that you have learned these results in your linear estimation or linear algebra also. Now, after introducing these vectors, let me try to explain you about the matrix. So, a matrix is simply a rectangular array of real number. These real numbers are arranged in a particular way inside the matrix, and every real number has an address, and this address is indicated by the location in a row and in a column. So, for example, in case if I try to write down here a matrix, say here like here A, which has element here as say A11, A12, A1n. So, these are the elements which are going to constitute the first row, and similarly these elements which are here like as here small a21, a22, a2n, they are going to constitute the elements in the second row. And similarly you can see here we have here elements am1, am2, amn, they are going to indicate the mth row. So, similar to the definition of rows, we have here the definition of columns. So, if you try to take here these elements a11, a21, am1, this is my here column. So, these elements are the elements of the first column, and similarly this a12, a22, am2, this is the second column. And similarly here you can see here the last column, this is here the nth column. So, you can see here that there are total here m number of rows and a number of columns, and this is indicated by the order of the matrix as say m into n or say m cross n. So, that is our symbol, that how are we going to indicate the matrix or represent a matrix. Now, in this matrix, if the number of rows and number of columns, they are going to be the same, that is m is equal to n, then this matrix A is called as a square matrix, right. And in case if you try to take the square matrix, that is m is equal to n, and in case if you try to take here all the elements on the diagonal like as a11, a22, here amm, which are non-zero. So, this aij is not equal to 0 for I not equal to j, and all the elements on the off diagonal elements, they are going to be simply here 0 like this one. Then this is called as a diagonal matrix, and this is represented by writing A is equal to DIAG and then A11, A22, AMM, right. Now, remember one thing, whenever we are talking of the diagonal matrix, it is not necessary that all A11, A22, AMM, that is the diagonal elements are to be the same. They can be same, they can be different, both the possibilities are there, right. Okay. Now, some important operations on this matrix and some related definitions. So, in case if I try to write down a matrix of order m by n, and then in case if I try to interchange the rows and columns, that means rows become column and column become rows, then this is called as a transpose of a matrix A, and this is indicated by A something like this symbol, which is here symbol of prime, or say this is called here as a transpose, right. So, in case if I try to take here a matrix here something like 1, 2, 3, 4, then the transpose of A is going to be the first row becomes the first column like as 1, 2, and the second row becomes the second column like as here 3 and 4, right. And in case the matrix and the transpose they are going to be the same, then this is called as symmetric matrix. For example, if I try to take here a matrix like here, say here 2, 2 and here 3, 3, right. So, in case if you try to change this, first row becomes here first column, and then in case if you try to take the second row, this becomes here second column. So, you can see here that both the matrix are going to be the same. So, this is called a symmetric matrix. So, in the symmetric matrix, the off diagonal elements in the lower diagonal and upper diagonals, they are the same, and a matrix whose all elements are 0, that means something like all the diagonal elements, all the off diagonal elements, they are all 0, then this is called as a null matrix, NULL matrix. And similarly, we try to define here an identity matrix. How it is defined? So, identity matrix is a square matrix. Suppose the order of the matrix is P cross P. So, we simply say that this is a square matrix of order P. So, in this case, all the diagonal elements are going to be simply 1, and all off diagonal elements are going to be simply 0. So, you can write down here, suppose if I try to write down here 3 by 3 matrix in which the all diagonal elements are here 1 and the off diagonal elements here are 0, then this is an identity matrix of order 3, or this is a matrix of 3 by 3 order. So, that is how we define the identity matrix. Now, in case if I try to observe here the different operations of this matrices and transpose, then are the two matrices of order m by n. So, A is of order m by n and B is of order m by n. So, in case if I try to sum A and B, and you know how to sum the matrix or say two matrices, right, their corresponding respective elements are added together. For example, if I take here two matrices 1, 2, 3, 4 plus here 5, 6, 7, 8. So, this is going to be 1 plus 5, 2 plus 6, 3 plus 7 and 4 plus 8, right. So, now in case if you try to sum the two matrices A and B, and can you try to take the transpose, this is equal to the sum of the transpose of the matrix, that is A plus B prime is A prime plus B prime, or A plus B transpose is A transpose plus B transpose, right. And about their multiplication. So, in case if I say A is of order m by n and B is a matrix of say order n by p, and suppose k is any scalar, then we can define here the A B transpose. That means, first you try to multiply A and B and then you try to take the transpose, that is equal to B transpose into A transpose. If you try to see here, the order of A into B is going to be m by n into n by p. So, this n and n they are the same. So, this order is going to be m cross p, and if you try to take the transpose of A B transpose, this will have an order p into m. Now, similarly, if you try to take here B transpose into A transpose, the order is going to be here p into n and then n into say here m. This n's are the same. So, this order is going to be of order p into m. So, you can see here that the multiplication is also valid, and similarly you can also verify that in case if we are trying to multiply a matrix with a scalar k and then we are trying to multiply b, then this is going to be the same as if you try to first multiply the matrix E with k and then you try to multiply it with here A into A times b. And this is same as if you try to multiply A and B and then you try to multiply the entire matrix by the scalar k, and this is going to be simply k into A B, right. And similarly, if you try to take here say three matrices A, B and C such that A is of order m by n, B is order of n by p and C is of order n into p, then I can write here A into B plus C as AB into AC, and similarly you can verify their order that this matrix multiplication is also valid, but you have to be very careful here with the orders of the matrices. Right. Similarly, if I try to take here three matrices A, B and C such that A is of order m by n, B's order is n by p and C has a order p cross q, then AB, that means first you try to multiply A and B and then you try to multiply by C. This is going to be the same as A into BC, right. And in case if you try to multiply any matrix by an identity matrix, then the matrix will remain the same. So, if A is the matrix of order say m by n, and in case if you try to take here any matrix here, say here A and then identity matrix of order here m. So, this identity matrix is of order m by m and A here is the order of say here m by n. So, that is going to be the same as A into the identity matrix of order n by n, and this is going to be the same here as a matrix here capital A, right. Now, there is another concept which is related to the matrix, that is about the trace of a matrix. So, the trace of a matrix is simply the sum of all the diagonal elements and the matrix has to be a square matrix. So, the trace of an n cross n matrix A, which is indicated or denoted by like writing TR and then inside the parenthesis A, or it is also written as a TRACE trace and then inside the parenthesis the name of the matrix A. This is defined to be the sum of all the diagonal elements, that is like this trace of A is going to be I goes from 1 to n summation A I I, right. And now, in case if you try to take here two matrices A and B and A is of order m by n, B is of order n by m, then trace of AB is equal to trace of BA. That is a very important result and you will see that we will use it in different places. And similarly, if you try to consider here a matrix A of order m by n and then try to define their product as say here A transpose A and then try to take the trace of A transpose A, that is simply going to be the double summation j goes from 1 to n, I goes from 1 to n, A square I j, and this is the same as trace of A into A transpose, right. And in this case, this trace of A transpose A and trace of A transpose, they are going to be 0 if and only if A is 0, that means A is a null matrix, right. And then in case if A is a n by n matrix, then trace of A transpose is the same as trace of A. So, these are very elementary results which you already have done in your matrix theory, but since we are going to use it, so it is important to have a quick revision. And similarly, there is another concept of rank of a matrix. So, you know that how to find out the rank of a matrix, that you have learned in your matrix theory course, but here I am more interested in using the results. So, the rank of a matrix A, which is of order m by n, is the number of linearly independent rows in the matrix A, right. Well, in case if you try to see that this rank is going to be associated with the different types of degrees of freedom of various types of statistical quantities. So, this rank is very important for us to understand here, right. The degrees of freedom definitely can be defined in various ways, but rank is one of the very important ways by which we can easily define and understand it. So, suppose B is any other matrix of say order n by q, then we define a square matrix of order m to be non-singular if it has a full rank. So, in case if you try to find out the rank of the matrix. If this comes out to be full rank matrix, then we say that the matrix is of full rank. And there are actually two results which we are going to use very frequently, that rank of AB is less than or equal to the minimum of rank of A and rank of B, and rank of AA transpose is the same as rank of A transpose A, which is same as the rank of A and which is the same as rank of A transpose. And then we have two definitions, say full row rank and full column ranks of a matrix. The matrix A is of full row rank if rank of A is equal to here m, which will be smaller than n. And A is going to be full column rank if rank of A is equal to n, which is smaller than m. So, we are going to use this concept of full row rank, full column rank a couple of times. Now, after that you also have learnt one definition, that is inverse of a matrix. So, you know that how to find out the inverse of a matrix. So, that I am not going to talk here, but definitely what are the properties which we will need, that I am going to give you here a brief overview. So, remember one thing, the inverse is defined for a square matrix as well as for a matrix which is not a square, that is a rectangular matrix. But usually unless and until specified, whenever we talk about the inverse of a matrix, we are going to talk about the inverse of a square matrix. And whenever you are trying to take a matrix which is of order say m by n, and if you want to find out the inverse of order m by n, then we usually use the concept of generalized inverse. And we also know that this generalized inverse are not unique. There is only one generalized inverse, which is Moore and Rose inverse. This is a generalized inverse, but this is unique, right. So, the inverse of a square matrix A of order m is a square matrix of order m, and which is indicated by A inverse like this, A, and in the superscript that we write -1. And this A inverse has been defined such that A inverse into A is the same as A into A inverse, and this is the same as identity matrix of order m, right. And the inverse of a matrix A exists only if A is non-singular matrix, right. And if you try to take the inverse of a matrix A, then this is same as here A, right. And if A is a non-singular, then in case if you try to see the operation of transpose and inverse, then the result is the inverse of a transpose, that is A transpose whole inverse, is the same as transpose of A inverse, that is A inverse and then whole transpose. And similarly, if A and B are non-singular matrices of the same order, then their product, well, if defined obviously, is also non-singular, and in that case we can write that A B whole inverse is equal to B inverse into A inverse, right. Then we also have learned that a matrix is called as idempotent matrix when the matrix is a square matrix, and in case if you try to multiply the matrix by itself, and the product is going to be the same as the matrix. So, in case if I say that capital A is a square matrix, then A is called as idempotent matrix if A into A, that is indicated by A square, that is also the same as A, right. So, in case if A is a n cross n idempotent matrix with the rank of A suppose equal to R, which is less than or equal to here say here n, then under this case the eigenvalues of A are 1 or 0, right. So, the eigenvalues of an idempotent matrix are always 0 or 1, and trace of A is the same as rank of A, which is equal to here R. So, that is the relationship between the rank of a matrix and the trace of a matrix. And in case if A and B are idempotent, means A is also idempotent, B is also idempotent, then AB is equal to BA, and then AB is also idempotent. So, if I try to consider here a matrix A that is idempotent, then in case if I consider another matrix which is defined as here I minus A, where I is here an identity matrix of suitable order, so that you can subtract it. So, then this matrix I minus A is also idempotent, and in case if you try to see here that A into I minus A, this is going to be here A into I minus A into A, and A into I is here A, and A into A here is A, which is equal to here 0, which is null matrix, right. And similarly, if you try to multiply I minus A into A, this will also come out to be a null matrix, right. Now, after this we talk about the quadratic forms. So, if I say if we have a matrix here A, which is of order here m by n, and suppose there are two vectors here, capital X and capital Y, and capital X is of order m by 1 and Y is of order n by 1. Then we try to define this quantity X transpose A y as double summation I goes from 1 to m, j goes from 1 to n, A I j x I y j, and where this the elements of this matrix A, they are non-stochastic, they are not random, right. Now, in case if A is a square matrix and symmetric matrix, then in case if you try to take here x equal to y, say x, then I can define here x transpose A x as A 1 1 x 1 square plus say here A m m x m square plus twice of A 1 2 x 1 x 2 plus up to here twice of A m minus 1 m into x m minus 1 into x m, and this I can write down here as simply here as a double summation I goes from 1 to m, j goes from here 1 to n, A I j x I x j. This is called as a quadratic form in m variables x 1 x 2 x m, or in general we simply call it that this is a quadratic form in x. So, this x transpose A x is indicating the quadratic form in x, right. Now, this quadratic form x transpose A x, this has got different definitions. So, this is called as positive definite if x transpose A x is greater than 0 for all x not equal to 0. This is called as positive semi definite if x transpose A x is greater than or equal to 0 for all x not equal to 0. This x transpose A x is called as negative definite if x transpose A x is less than 0 for all x not equal to 0, and the quadratic form x transpose A x is called as negative semi definite if x transpose A x is less than or equal to 0 for all x not equal to 0, right. So, and one of the possible ways to check whether the quadratic form is positive definite, negative definite, positive semi definite or negative semi definite is that you try to find out the characteristic roots of the matrix A, and if all the characteristic roots are coming out to be greater than 0, that means the quadratic form is positive definite, and if the eigenvalues are coming out to be greater than or equal to 0, then this is positive semi definite. If all the eigenvalues are coming out to be negative less than 0, then it is negative definite, and if all the characteristic roots or say eigenvalues they are coming out to be less than or equal to 0, then this is called as negative semi definite, right. And similarly, if I try to consider one more matrix here P, which is non-singular, and capital A is any positive definite matrix or say positive semi definite matrix, then P transpose A P is also a positive definite matrix or positive semi definite matrix. So, in case this is positive definite positive definite matrix, then it is positive definite matrix, and if it is positive semi definite matrix, then it is positive semi definite matrix. Now, you already have done this topic, but I will just try to have a quick revision. That is about simultaneous linear equation. So, we know that in case if we have got say m linear equations in n number of n nodes, say x 1, x 2, x n, and suppose this a I j and say b I, they are some scalars, known scalars. So, I goes from 1 to here m, j goes from here 1 to n, and these m linear equations are of this form, like as a 1 1 x 1 plus a 1 2 x 2 plus a 1 n x n is equal to p 1. Then a 2 1 x 1 plus a 2 2 x 2 plus a 2 n x n is equal to b 2, and so on. We have here the a m 1 plus x 1 plus a m 2 x 2 plus a m n x n is equal to b m. So, you can see here this these equations can be written here as like this a 1 1 a 1 2, see here a 1 n, all these coefficients will come here a m 1 a m 2, see here a m n, and then we will have here all the see here unknowns x 1 x 2 here, see here x n, and then this is equal to here, see here b 1 b 2, see here b m, right. So, this is indicated by here a, this is indicated by here x, and this is indicated by here see here b, right. So, all these equations can be written in the form of here x equal to b. So, obviously, A is a real matrix of known scalars, and this is of order m by m. This is called as a coefficient matrix. X here you can see this is a n cross 1 real vector, and b is a m cross 1 vector of known scalars, right. Try to see here, I can express this a x and b here like this, right. So, they are the same thing which I just shown you. So, now in this case if A is a n cross n non-singular matrix, then A x equal to b has a unique solution. That means, you can obtain the values of x 1 x 2 in a unique way. And similarly, if you try to create here an augmented matrix like as here A and small b, and suppose this is indicated by here capital B. So, capital B is an augmented matrix. Can a solution to A x equal to b exist if and only if rank of A is equal to rank of B, and if A x equal to b is consistent, then A x equal to b has a unique solution if and only if rank of A is equal to here n, right. Okay, so, now we come to an end to this lecture, and I have tried my best to collect here some smaller results which I am going to use in the forthcoming lectures. But I will request you that you try to have a look into your books and try to revise these results, because I have given them here very briefly. My idea is just to update you, but you need to have a detailed knowledge of these results. So, you try to have a look, try to revise it, and I will see you in the next lecture. Till then, goodbye.